Thank you for joining this presentation that is dedicated to a membrane-based technology named MAF-technology for algae harvesting and medium reuse. I am Leen Bastiaans, Project Manager at VITO, a research institute in Belgium that is focusing on applied research. In search for new renewable chemicals, algae is one of the biomass types that is considered. As is depicted well in the infographic of the Interreg Northwest Europe project IDEA, that is coordinated by VITO, an algae-based value chain consists of different parts that are organized at the algae farm level, at algae processing level, as well as with the formulating industry. This presentation will focus on the harvesting part that is situated at the algae farm level and that is linked with algae growth, medium reuse, as well as the logistics toward the processing. At harvesting time, the algae concentration in the medium is on average situated between 0.5 and 2 grams of dry algae per liter. This represents less than 1% of the medium, implying that more than 99% of the medium consists of water and cells. For this reason, harvesting of microalgae refers to a dewatering process, and the reuse of the medium is required in the perspective of sustainability, especially at larger scale. At research level, algae can be harvested with discharge of the medium and preparation of new medium. However, to avoid excessive water use, discharge of salty water, and costs of new salts in case no seawater is near, reuse of medium is a must to operate algae farms. At VITO, a submerged membrane-based technology was developed that offers a solution for the harvesting and medium reuse. MAF stands for Membrane Algae Filtration and is a computer-controlled submerged membrane-based technology for integrated pre-harvesting of microalgae and medium reuse. The heart of the technology are the submerged membranes that enable to produce algae-free permeate via under pressure, without the need to apply shear forces on the algae biomass. The MAF device can be connected directly to algae cultivation reactors or buffer tanks according to the needs, and produces on the one hand a permeate that comprises water and nearly all the salts, and that can be reused immediately for the algae cultivation with addition of some nutrients like nitrogen and phosphorus. On the other hand, a pre-concentrated algae biomass is generated that can be further concentrated when required using a centrifuge or other technologies. With a pre-concentration factor of 10 to 20 times, as indicated in this example, 90 to 95% of the water can be reused. This photo illustrates the output of the MAF, being on the left partially concentrated algae and on the right-hand side algae-free permeate. The MAF technology has been evaluated practically using devices of different sizes. The picture illustrates, as an example, a small MAF linked to 1500-liter bioreactors in a sun-built infrastructure in Belgium. The MAF was integrated as illustrated in the previous slides, being connected directly to the bioreactor. A continuous harvesting was applied based on turbidity. As such, the MAF also acted as a turbidostat to keep algae at the same density, which can be favorable for the algae growth. The collected test data confirm that the water reuse and salt reuse is situated between 90 and 95%. The algae densities that were reached exceeded the expected values of 10 to 30 grams of organic matter per liter, as values above 60 could be obtained. Reuse of the permeate as medium was realized and no negative impacts were observed on the algae growth. Within the IDEA project, the MAF was applied for different algae species, in batch or continuous mode, and upscalings were realized. More specifically, the MAF technology is being developed in two directions. On the one hand, there were actions to increase the TRL. Research prototypes up to devices with 10 square meters of membrane for daily harvesting ranging between 50 and 3000 liters have been realized within IDEA. In parallel, translation to commercial prototypes was initiated. On the other hand, the application area of the MAF is explored by evaluating different algae species. The early MAF trials were performed mainly with Nanochloropsis, but meanwhile, different algae species were evaluated like Chlorella, Synedesmus, Chloromonas, Rhodomonas, and Pavlova. They were all found suitable for harvest with MAF. In the remaining part of the presentation, I would like to focus on Rhodomonas as an example of fragile algae. Rhodomonas is a saltwater microalgae species. It does not have a protecting cell wall and is as such very fragile. This makes it a relevant test species to evaluate the low shear MAF harvesting technology. Rhodomonas has an interesting fatty acid profile with EPA as well as DHA as omega-3 fatty acids. Rhodomonas is used in aquaculture for live feed applications of copepods that serve as feed for fishes. The Rhodomonas biomass used in this study was cultivated by HZ in Vlissingen as part of the Velgras project, and the concentrated biomass is being used in the same project by ILVO for taste trials. A first key question was whether Rhodomonas cells remain intact during harvest with the MAF device. For this purpose, off-site batch tests were performed at Vito with 125 liters of Rhodomonas culture. The integrity of the cells was monitored via microscopy and visual observation of the permeate. Macroscopic analysis visualized the concentration of the cells, and as algae cells remained mobile and the permeate colorless, it was concluded that the Rhodomonas cells remained intact. These data indicate that the MAF technology offers also potential for harvest of fragile algae species. Next, we try to evaluate how many times Rhodomonas cultures can be concentrated by treating a larger volume of Rhodomonas culture, being 420 liters. The density of Rhodomonas cultures is generally relatively low. In this case, it was estimated to be 0.2 grams per liter at the start. A cell-free medium was produced during the concentration, and the biomass was concentrated 100 times by reducing the volume from 420 liters to about 4 liters. Fluxes at that time were still fine, indicating that with larger patches of algae a higher concentration factor can be reached. As such, for Rhodomonas, high concentration factors are feasible. Also for Rhodomonas, an on-site MAF trial was performed. MAF equipment was transported from Vito to Vlissingen and installed in the greenhouse for connection to Rhodomonas photobioreactors. In total, 520 liters of algae culture were reduced to 5 liters, implying a volume concentration factor of more than 100. This fitted well with the biomass estimates as determined via flow cytometry. The harvested Rhodomonas was intended for taste trials, where reduction of the salt content in the biomass was desired to avoid a dominating salty taste. Therefore, just after the harvest, the MAF device was also used to desalt the Rhodomonas biomass via diafiltration. This refers to a process where salts are washed out by flushing the concentrated biomass with fresh water. When applying this process, the electric conductivity was reduced 15 times. This step was coupled with an additional up-concentration of the biomass to a final 10 grams per liter, realizing a final volume concentration factor of 131. Finally, the Rhodomonas biomass was freeze-dried for storage until taste trials are organized. I would like to end with some take-home messages as a conclusion. The MAF technology integrates pre-harvesting of algae and medium reuse and provides, when required, also turbidostat and a desalting function. The MAF has been demonstrated to be applicable for different algae species. In the presentation, I elaborated on Rhodomonas as an example of a fragile algae that can be harvested with the MAF technology. The cells remained intact and high volume concentration factors could be reached. Thank you for your attention and feel free to contact us in case you have questions.